What's up? If that song doesn't get you pumped up to do math, I don't know what will. Let's get into it. Alright, remember, take some notes, rewatch the parts that are confusing, and ask questions, and write them down so you don't forget them. Alright, rational exponents. What are they? Well, we learned about rational numbers, right? They were just numbers that could be expressed as a fraction, m over n, where m and n are integers. Rational exponents are just exponents that are fractions. So, they have a lot to do with the exponents that we learned about 2 videos ago, and a lot to do with radicals. So, when you have your exponent, m over n, the numerator works like an exponent, an integer exponent. So if you have a 2 in the numerator, it's like you're squaring the number. If you have a 3, it's like you're cubing it. The denominator works like a root, right? It's like the index of the root. So if you ever see something like a to the 1/2 power, that's the same exact thing as the square root of a, alright? A to the first. So let's do some examples. Alright, first let's start off easy without any variables. Let's simplify these numbers being raised to rational exponents. So again, remember, the numerator is the exponent and the denominator is the root. So this is the same thing as the cube root of 8, alright? And we know that's 2, because 8 is 2 times 2 times 2. So you want one of those 3 factors. So the final answer is 2. Right? 16 to the 3/4 means if we were to break down 16 into 4 equal factors, take 3 of them. Alright? So the answer is 8. Now another way to look at it is to take the root first and then cube it. Alright, that's going to be the theme for all of these. When you're simplifying using rational exponents, take the root first, make the number smaller, and then raise it to a power. So the 4th root of 16, you should know, is 2, because 16 is 2 to the 4th power. So like 2 to the 4th power to the 1/4 power would just simplify to 2. And then you cube it, and you get 8. Alright? 9 to the 3/2 power. We can rewrite that as 9 to the 1/2 power cubed. Remember, 1/2 power just means the square root. So that's 3. And then we're going to cube it. And then 27. Alright, so just take the root first and then raise it to the numerator power. So this right here would be like the square root of 4 to the 5th power. So it's like 2 to the 5th. And that becomes 32. 27 to the 4/3 power. Take the cube root first. That's going to be 3. Raise it to the 4th power, and you get 81. Alright, so these should be done without a calculator. We'll learn how to use a calculator later, but for now, we're doing these in our head. 1 to the 3/4 power, well, it's just going to be 1, because the 4th root of 1 is 1, because 1 times 1 times 1 times 1 is 1. And then you cube that, and that's going to come out and be 1. Alright, negative 32 to the 3/5 power. That is the same thing as negative 32 to the 1/5 power cubed. Negative 32 to the 1/5 power is just going to be negative 2, because negative 2 times itself 5 times is going to be negative 32. And then cube that, and it's going to stay negative, and you get negative 8. Alright, last but not least, 49 to the 3/2 power. Do not try to cube 49 and then take the square root. That would be way too hard to do without a calculator. So instead, we're going to take the square root of 49, which is just 7, and then cube it. Alright, and 7 times 7 times 7 is going to be 343. Alright, so let's move along. Alright, these are the properties of radicals that we learned yesterday, and we can kind of quickly prove them by using rational exponents. So when you have number 1, the nth root of a to the mth power, that would be the same thing as a to the m over n power. And you can kind of rewrite m over n as 1 over n times n. So we can write that in our exponents. And we can put some parentheses in there and see how it's like the power of a power rule. And then you could rewrite a to the 1/nth power as the nth root, and then raise that to the nth power. Alright, so this first property just shows that you can take the root or raise something to a power in any order. Alright? And in this next example, if we remember our exponent rules and just apply them, we have this right here, which is the nth root of a times b. So that's the same thing as a times b to the 1/nth power. Alright, and we know from our exponent rules we could just apply the 1/nth power to the a and the b. And then if we were just to rewrite them in radical form, we see that this, the nth root of a times b, is equal to the nth root of a times the nth root of b, which is just saying you could multiply or take the root in any order. Same thing with division, right? We learned about the radical rules, how you can divide or take the radical in any order. It's kind of the same idea. If we started on the right side here, we have a over b. If we write that with a rational exponent instead of the nth root, if we wrote it as to the 1 over n power, we can then apply our exponent rules and rewrite that as a to the 1/nth over b to the 1/nth. And then rewriting them with rational exponents, going from rational exponents to radicals, we get that. Alright, let me just clear this real quick. Power of a power. Here's why you multiply indices. Alright, if we were to take this left side here and rewrite it with rational exponents, so instead of writing the nth root, we're going to write it as a to the 1/nth power. And then instead of taking the mth root, we can write it as raising it to the 1 over m power. Well, it's power of a power, so that's why we're going to multiply these two fractions. And you get a to the 1 over m times n power, because that's what these two fractions will multiply together, and that you'll multiply across and get 1 over m times n. Alright, and then that just becomes the m over n root of a, because the denominator of a rational exponent is the root that you're going to take. Alright, here, if you had, say, like a to the 1 over n power to the nth power, if you multiplied these two together, because it's a power of a power, you'd get a to the n over n power, and we know n over n is just 1, and you just get a. Alright, and the last two we talked about when you use absolute values in the last video, so no need to go over that again. Alright, let's apply these right here. So 64 to the n to the 12th power to the negative 1/6 power, we could just do the power of a power. Now, you have to be careful and make sure we don't need absolute values. Alright, remember, if you take the even root, and this 1/6 power would be like an even root of something with an even exponent, and it comes out to have an odd exponent, then you want to use absolute values, which we will not need here because it's going to come out to an even exponent. But in the next example, we'll need absolute values. So we're going to apply the negative 1/6 to both the 64 and the n to the 12th. So 12 times negative 1/6 will give you negative 2. So then we can rewrite that as 1 over 64 to the 1/6 times n squared. And again, you took the even root of a variable with an even exponent, but it came out to be even. So it wasn't even odd. So we don't need an absolute value here. And then that 64 to the 1/6 power, we can reduce that to 2. So it becomes 1 over 2n squared. Alright, in number 32, it's just like taking the square root of 81m to the 6th. It's the same thing, different notation. So we're going to take the square root of 81, or raise 81 to the 1/2 power, and then take m to the 6th and multiply that 6 by 1/2 and get a 3. So look what happened. We took the even root of a variable with an even exponent, and it comes out to have an odd exponent. So we get 81 to the 1/2 power, that's just 9, and then m cubed, so that's going to be the absolute value of m cubed. And boom, that's the final answer. Last one, a little more complicated, but again, it's just like these exponent problems we did 2 videos ago, except now you have fractions. Alright, so we're going to take everything inside the parentheses and apply the 5/4 power. X to the 11 times 5/4, you could multiply that and you get 55/4. And then y squared to the 5/4 power, that's become y to the 10/4 power, over 81 to the 5/4 power, over x to the 15/4 power, over y to the negative 10/4 power. Alright, now it may have been easier to simplify what was inside the parentheses first, but it really doesn't matter. As long as you just do one rule at a time and don't forget anything, you'll be fine. So now, let's clean this up a little bit. So 16 to the 5/4 power, if you take the fourth root of 16, that's 2, raise that to the 5th power, we get 32. Let's ignore the variables for a second. And 81 to the 5/4 power, fourth root of 81 is 3, raise to the 5th power, and you get 243. Now, we're going to use our exponent rules here. So if we look at the x's right here, we can just subtract these exponents because it's the same base. So x to the 55/4 divided by x to the 15/4. If you subtract 55/4 and from that subtract 15/4, you're going to get 40/4. And that's going to stay in the numerator. And we know it's going to reduce to 10. We'll do that in a second. And then this y to the negative 10/4, we can bring it up to the numerator and make it y to the positive 10/4 because we want to get rid of negative exponents. So if you have a variable with the negative exponent in the denominator, bring it up to the numerator. And you get y to the 20/4. Alright, our final answer is going to be 32. And then simplify this 40/4, make it x to the 10th, 20/4, make it y to the 5th, over 243. And that's the final answer. And let's make sure we didn't need absolute values here. We took an even root over here, the fourth root of this y coordinate, this variable of y, which had an even power, so it's going to turn positive, but it came out to have an odd exponent. So let's throw some absolute values around that y. Alright, pretty much if you raise anything, any variable, and you take an even root of it, and it ultimately comes out to have an odd exponent, you're going to need absolute values. With this x to the 10th, you don't need it because it's going to stay positive no matter what. Alright, believe that is it. That's the last slide. Cool, thanks for watching, and see you in class.